Like any good chemistry class, we at some point need to talk about Paula Abdul and the fact that opposites attract. What we're going to be doing is we're going to be talking about something called molecular polarity and use that as kind of a way to introduce a little bit of a pretty important topic in chemistry called solution chemistry. So what is it about Paula Abdul that made this old fart's heart go pitter patter? Well, you're going to find out in just a second. One of the things I have to mention is that I have lied to you a little bit. We have been talking about covalent bonding, and we've talked about the fact that it's the sharing of electrons. And actually, up to this point, what I've done is I've kind of led you to believe that everything was considered a nonpolar covalent bond. And what I mean by that is that a covalent bond that is considered nonpolar is a completely equal sharing of electrons. So just to kind of show an example of this, here is elemental iodine. There's two iodines, and we talked about the fact that this little line is actually representative of two electrons being shared. It is true that iodine is considered a nonpolar covalent bond because two iodines are able to pull equally on those two electrons. And so, in a sense, there is no one that really wins the tug of war. But the situation that I kind of lied to you about is that it's very common that when you are sharing electrons, you end up with something that is considered polar. And this is something where even though you are sharing two electrons, it is kind of an unequal sharing. So a really great example of that is with something like hydrogen iodide or hydroiodic acid. And it turns out that if you look at these two nuclei, iodine has a whole bunch of protons, and those protons are really, really good at attracting electrons, a little bit stronger than hydrogen's one wimpy proton. So what actually ends up happening is that you get a little bit of an excess of electrons on iodine relative to hydrogen. And what this does is it produces something called the polar covalent bond that's represented like this. And you'll see this kind of like, it kind of looks like a cursive D with a squiggle. This is actually a lowercase Greek delta, which is the way that chemists will often represent this kind of situation. And what that's telling you is because electrons are negatively charged and the fact that these two electrons are pulled more towards iodine, you actually end up with a slightly more negative side for hydroiodic acid over here on the iodine than you do over here. And so the case is that where you have more electron density, you end up with a negative charge. Where you have less, there's a positive charge over there. And this is something called a molecular dipole. This situation is actually an electrostatic dipole, or electric dipole is another way of saying it. It turns out in physics there's a couple of different types of dipole. It's really popular to represent magnets, for instance, in a magnetic dipole. So if you kind of understand this idea of like a north-south magnet, you also understand this idea of an electric dipole. It's just that it has to do with electric charge and not magnetism. So what we have to talk about now is how you decide if a bond is actually a situation where you're pretty much equally sharing those electrons in the bond, or you end up with a polar covalent bond where you've got kind of a separation of a little bit of positive and a little bit of negative, or a case like an ionic compound where you've got a full positive and a full negative. So we kind of know already how to predict if something is ionic. Those are those things that are made up of, or sorry, those compounds that are made up of metals and nonmetals. What about the covalent compounds that are made up of two nonmetals? How do we decide that? Well, it turns out what we do is we once again use the ultimate cheat sheet in the universe, this thing called the periodic table. And it turns out that things that are kind of more up and to the right here, with the exception of the noble gases, they kind of don't play. We already know that they don't like to form bonds. But if you look up and to the right on the periodic table, it is said to increase in electronegativity. And electronegativity is nothing more than the ability to attract electrons in a covalent bond. So in your resource guides, you'll find something that looks like this, which is an electronegativity table. And one of the things you'll notice is that, first of all, that in this particular table, the noble gases are left off because they kind of don't play the game. And you'll also notice the most electronegative element is fluorine, which there's different ways that you can measure this. This is the way that we're going to measure it in this class. You notice that we've got that fluorine at about 4.0. And so if that fluorine tends to bond with something that is not a very good polar, or something that's not very electronegative, let's say like hydrogen over here at 2.1, that difference of like 1.9 is actually enough to create what's called a polar covalent bond. What we're not going to talk a whole bunch about in this class is kind of what happens when it's not just a simple two-part bond, right? So it's not just a hydrogen connected to a fluorine. What if it's like something that's made up of a whole bunch of different elements, all kind of connected together in a really particular geometry? That we talked about the geometries, but it turns out that the answer is a little bit complicated. For us, we're just going to kind of simplify things just a little bit, and I'll show you kind of some examples of things that we're going to consider polar, and just a little bit of insight as to how we actually figure that out. So it's important that you know that on that periodic table that electronegativity increases as you go from left to right across a row, and then bottom to the top of a column. So the way that I always remember this is just remember that fluorine is the biggest and cesium is the smallest. There are a couple that are down here that are left off the table, but it doesn't really matter because they're metals anyway. But really what you're going to do is you're going to look at the difference in electronegativity for these simple compounds. Here's another way that we can represent it. The electronegativity differences are all represented here. And one of the things you'll notice is that the things with a huge electronegativity difference, like this HF bond, right? It's said to have a huge dipole, right? 1.82 is measured in dBis, but you probably don't care about that. We just kind of care about the relative magnitude of these numbers. And you'll notice that as you kind of work your way down the table, each one of these is bonded to an H. Eventually you get to this point where, yeah, this is actually enough of an electronegativity difference to still be considered something that has a dipole. In other words, it still has that separation of positive and negative charge, but it's definitely less of a separation of positive and negative charge. So this gives rise to a whole bunch of different physical properties that we could talk about over the course of like an entire year. But what we're really interested in is what effect it has on solubility. So we're going to kind of build this discussion into what it has to do with solubility. But before we do that, I just wanted to show you a couple of real examples of molecules and show you a couple of different representations for how we represent this thing called of polarity. So this little arrow right here, the thing that kind of looks like an arrow you just grabbed out of a quiver that's got a sharp end and this plus end, is another way that we represent things that are polar, right? So HCl is a polar molecule. Look, it's even labeled for you. And so when we see a dipole arrow like that, it's telling us that this side is a little bit more negative, right? Wherever the arrow is going to is a little bit more negative. And then the thing where even that little thing kind of looks like a plus, the thing where that is a kind of a little bit more plus charge. Keep in mind, we're talking about a partial positive and a partial negative. If we just completely severed this bond altogether and just made hydrogen just straight up positive and chlorine straight up negative, that would actually be an example of an ionic compound, right? And so HCl gas is muriatic acid. And so that can actually happen. But in this case, the HCl is still together, and you consider that thing a really polar molecule. There are examples where you might have like something that's got three polar bonds that are all kind of like oriented perfectly, that end up kind of balancing out the pull of everything. So this thing actually tends to be nonpolar, this boron trifluoride. And that is kind of a really special situation that really is only going to happen in chemistry class. And I'm not going to beat you up with it too much, just because we're not going to kind of connect the two together between geometry and the way these polar bonds are. Really what I want you to do is I just want you to be able to recognize an individual polar bond and maybe not recognize like polarity based on those electronegativity differences coupled with geometry. It gets really, really complicated. And I'm trying to be a little nicer to you guys. For us, if we're going to talk about a covalent molecule that has either a nitrogen or an oxygen, especially nitrogen and oxygens in carbon-containing compounds, we're going to just go ahead and call that polar. Here's another example of something that is polar. It turns out that when you look at electronegativity differences between carbons and hydrogens, even though there is a really small difference in pull, notice that this is not represented with any kind of dipole arrow. This thing is called the dipole arrow. It's a way of representing polarity. So anyway, C and H, if you look at it on the resource guide, you'll notice that the difference is really small. That small difference isn't enough to actually make these bonds right here polar, but the fact that C and Cl have a different enough value that this is actually considered a polar bond, and that makes this whole entire thing polar. Here's just another example of something that's overall nonpolar because it's got 4 bonds pulling in equal and opposite directions. If you're having any kind of problems understanding, where all this polarity comes from, this is a really good, helpful animation that you can kind of play around with and see what affects it. But the real thing that I wanted to get to today is, why do we care about this thing called molecular polarity? Well, it turns out that polarity really determines solubility. And just about everything in this universe we kind of know is essentially a mixture of some kind. So it's important for us to kind of understand the forces that are at play if we're going to really understand what matter is doing in our everyday life. And solubility, you probably know, is the measure of one substance's ability to dissolve in another. And the thing that dictates what does this is the actual polarity of the two substances. So in other words, if you have polarities that match, right, say something that's a polar covalent molecule that's trying to dissolve in a polar covalent molecule, it's really likely that that is going to successfully dissolve. But if you have something that's totally nonpolar, that doesn't have that kind of separation of plus and minus charge, well, it turns out that those things tend not to dissolve in things that are polar. So the really typical example of this is, why doesn't oil dissolve in water? Well, it turns out that oil is a really nonpolar compound. It doesn't have any separation of charge. And it is really bad at dissolving in water because water has a huge separation of charge, that partial positive and partial negative side. So it's said not to dissolve in each other. It's not a miscible situation. Whereas water is easily able to dissolve something like sugar, which is another polar covalent molecule. And so chemists just kind of simplify this by saying like dissolves like, but you can really read that as polar things dissolve polar things, and nonpolar things dissolve nonpolar things. So again, Sean, why do we care about this polarity thing? Well, to give you kind of another vocabulary word, this idea of polarity has everything to do with how strong these things called intermolecular forces are. These are the forces that kind of hold separate molecules together like glue. And it always has to do with Paula Abdul, right? This idea that opposite charges attract. If you have positive and negative charges, you are going to be really happy to interact with other positive and negative charges. Specifically, a negative interacts with a positive interacts with a negative, blah, blah, blah. But it turns out just about any physical property that anybody really cares about can be understood if you kind of understand these intermolecular forces. And there's a bunch of different ones that we're not going to talk about specifically, but it's important that you kind of understand that's the way that just about all matter kind of holds itself together through these kinds of positive-negative interactions. It would also be a good time to have the solution vocabulary resource guide in front of you. It'll be kind of help to organize this blabbering I'm doing at you here. But before we do, just be reminded that we've got this idea of a mixture being represented as either a heterogeneous or a homogeneous mixture. And the things that really separated the heterogeneous and the homogeneous is the idea that the homogeneous was uniform throughout, right? So we've already talked about this in the very first week. And so we call that thing a solution as well as a homogeneous mixture. And those two things are made up of both solutes and solvents. So hopefully you have some memory of going through this stuff. And when you take a look at the definition of a solvent, that's going to be the substance present in the greatest amount and then the solute is going to be the substance present in the lesser amount. So as an example of, say, salt water, right, that would be something where sodium chloride is the solute and the solvent is water. Another way you might say that is that a solvent does the dissolving, and then a solute is the thing that is dissolved. A great question at this point is, why does that separation of charge, that dipolar, that fact that these things are polar compounds, kind of tend to have one polar compound dissolve in another polar compound, right? What's really going on with this whole Paula Abdul effect, right? That positive and negative interaction. By the way, I should mention one thing that has in the past confused students is that when I say polar in this case, that actually includes both polar covalent, in other words, things that are unequally sharing electrons, and ionic compounds, right? And so ionic compounds are kind of like the most extreme version of polarity, because they have a full separation of positive and negative charge, not just a little bit, right? And so that's an important distinction to make. And I could keep talking at you, and I definitely will keep talking at you, but there's a couple of animations out there that I think do a pretty good job of kind of showing you the whys behind what's going on here. When you click on that link that you just saw, hopefully this animation will come up. And what this is going to represent is what water is going to do in the case where you add something that's ionic to it, right? Something that's like super duper polar. What is it about this polar water molecule and that super duper polar ionic compound that result in it dissolving? So let's just watch what happens. So as we zoom in here, we can see the way the cations and anions are stuck together. And then what you'll notice, if I pause it for a second here, well, I guess I can't pause it, but you'll notice that water has both a negative and a positive side. The positive side tends to interact with the negatives. You can see the hydrogens are kind of stuck to that guy. And then for that positive, you'll see that big red sphere is attached to it, and that's the oxygen. And so what we have here is that negatively charged oxygen, or partially negatively charged oxygen, interacting with the cation. And then you have the Cl minus anion that's interacting with the hydrogens that are slightly positive of the water molecule. So notice that when it comes to the positively charged cations, the oxygen of water is always attracted to that because the oxygen is slightly negatively charged. And then if you look at these Cl minuses, there's always a hydrogen of water kind of interacting with it. See, there it gets carried away again. So that kind of gives you some insight to why something might dissolve that has that separation of positive and negative charge. This next animation, you'll notice a couple of differences. This is going to be sugar, which is a polar covalent molecule, dissolving in water, which is itself, as we talked about, a polar covalent molecule. But you'll notice a couple of differences between this and what we saw for the ionic compound dissolving. So macroscopically to our eyes, this is what we're going to observe, right? When sugar dissolves, it's going to look to our eyes the same macroscopically. But when you really zoom in, you'll notice one big difference here is that, first of all, is that the molecule itself kind of stays together, right, as it gets carried away. It's a similar thing in that this polar sugar molecule has an oxygen in it, right, which has a really great ability to attract electrons, and carbon and hydrogen aren't so good. And so you still get this kind of positive charges on water interacting with negative charges on sugar, but it's a little bit different in that the covalent molecules tend to kind of stay stuck together, right? There's not the cation and anion that kind of separates apart. And that's kind of one big important thing in terms of the differences between ionic and covalent molecules and the way that they dissolve. And this next example will kind of be a particle diagram kind of look or a zoom in on what happens when oil doesn't dissolve in water, right? Something that is a nonpolar compound not being able to dissolve in a polar compound like water. Here we have the oily substance known as hexane. By the way, you'll notice it's nonpolar because it's only got carbons and hydrogens, and those don't have an electronegativity difference that's enough to actually have a separation of charge. And then you have our old friend water over here, and we can kind of watch what happens. And so here we have those hexanes floating around and the water floating around. And you'll notice that they just kind of ignore each other. And what you'll notice in a second is that what happens is that water essentially is going to kind of be attracted to itself through those same positive and negative interactions. And it's going to kind of force the oil not to be able to participate in this. And so you can kind of see the nonpolar thing kind of hung out together. All the little water molecules are kind of hanging out together. And so they don't want to play together. And what we end up with is this thing called a heterogeneous mixture, right? Where the oil layer is on top and then the water layer is on the bottom. And there we see that separation of phases. On that solution vocab list, there's a couple other things that we should kind of have down as we kind of work through the rest of this week. First of all, this idea of a saturated solution. This kind of gives you the idea that solutions can only mix up to a certain point. Eventually, you get to the point where you saturate the solution, meaning that you really can't get any more solute to dissolve in a given solvent. And every kind of homogeneous mixture has this kind of idea of being able to saturate it. Turns out there's this other thing called an unsaturated solution where essentially you just can fit more solute. And then there are examples of things called supersaturated solutions that we're not going to talk a whole bunch about, even though it gives rise to some really cool demos that we could have done in class. But oftentimes people will say that something is a saturated solution, but really not be correct about it, right? It's actually a heterogeneous mixture. Because what happens when you hit that saturation point of something, if you try to add more solid, it's just going to not be able to go into solution. And we've all kind of seen that when we've tried to make our drinks too sugary. At least I have, the diabetic. Other bits of vocabulary, you probably have heard the word miscible. That's specifically two liquids that dissolve in one another. So you would say, for instance, that ethyl alcohol and water are miscible in, say, Absolute or something like that, the vodka. And then things like oil and water would be said to be immiscible because one liquid is not dissolving in another. Any of you that go on to take A&P, a lot of you probably will, you'll be talking a whole bunch about these things called electrolytes. For us, these are just ionic compounds that dissolve in water. It turns out that they'll conduct electricity. Water normally doesn't conduct electricity until you dissolve some sort of ionic compound in it. So electrolytes, it's important to know that ionic compounds dissociate into cations and anions. That's what we saw in that animation where the cations and the anions both kind of broke apart due to the influence of water. That's called dissociation. Turns out that this allows them to conduct electricity and do a whole bunch of other important things in the body that you'll talk about ad nauseum in A&P. So one thing that you really need to know about is this idea that covalent compounds and ionic compounds dissolve differently, even when their polarities match. Ionic compounds always dissociate, right? That means they break apart into cations and anions. Those are called electrolytes because they conduct electricity in solution. And it turns out that the more you dissolve, the more strong you are as an electrical conductor. Covalent compounds do not dissociate when they dissolve, and for this reason they're called non-electrolytes because they don't conduct electricity in solution. And then I would be failing you miserably if I didn't tell you about the movie Idiocracy, so I would definitely recommend you watch what they had to say about electrolytes. In the very near future, when we start to talk about calculating with concentrations of solutions, you're going to learn to love these things called solubility curves. I just wanted to throw in a couple to kind of show you some differences between the way different things interact in the presence of like higher and higher temperatures. One of the things you'll notice is just about everything that is a solid tends to increase its solubility as you increase the temperature. So we'll talk a little bit more about what does it mean, this whole grams of solute per 100 grams of water, and we'll do all kinds of fun calculations at some point. For now, just recognize that different compounds have a different effect in terms of how they react to temperature. The degree is different. Like in other words, some have a huge increase in solubility as temperature increases. Some not so much, right? So you'll see kind of like salt water doesn't really do too much, but it definitely does increase a little bit. And then things like potassium nitrate kind of go through the roof. Another interesting thing to take a look at is this, which is ammonia. And you'll notice that this is kind of an interesting phenomenon that happens with gases, right? When you increase the temperature of a gas, when you increase the temperature of a solution of a gas dissolved in a liquid, what happens is the gas will actually go down in solubility. So that's like a really important thing to know, is that solids tend to increase in their solubility at higher temperatures, and gases do the exact opposite. Those of you folks, like I'm really into fly fishing and stuff like that, and so you can really screw up a stream bed with really, really warm water because there's literally not enough O2 gas for the fish to breathe. Other things to just talk at you about are different factors that affect solubility. We just saw the effect of temperature on it. But there's actually two things that are like sometimes difficult for students to keep track of, is this idea of like the effect on a total solubility relative to just the speed of dissolving. So I just listed out a couple here that you could know about. And so probably the most important thing that affects solubility, especially total solubility, is that idea of like dissolving like, right? Differences in polarity have a huge role to play. We saw that the temperature, when solids are dissolved in liquids, usually the solubility increases when your temperature increases, and then gases show the exact opposite effect. In terms of the speed of dissolving, you've probably made Kool-Aid before and stirred that Kool-Aid, and the reason for that is that stirring tends to kind of speed it up. It doesn't, however, really affect the total solubility. Like you'll never get more sugar dissolve just by stirring. You just kind of increase the speed by which it dissolves. Obviously, if you have like really chunky Kool-Aid and stuff like that, it's going to take a little bit longer for it to dissolve relative if it's this really nice little powder. And it turns out temperature will also increase the overall speed of dissolving. And then in the case of gases specifically, there's this really interesting pressure effect. So if you increase the pressure of a gas, it does actually increase its solubility. And a classic example of that is like when you have a pressurized container of soda or something like that, you won't notice any bubbles. And the second that you relieve that pressure, right, all that gas kind of tries to escape. So this is an example of where you really can affect the solubility of something just by the amount of pressure. And this last set of slides is just another example of some solubility curves. I included this just because it shows you that not all gases have kind of the same extent of their the effect of temperature on their solubility. Probably not terribly surprising, but there's that idea that oxygen, as the temperature increases, the amount that's able to dissolve gets smaller and smaller. So I think I've droned at you enough. So I'm going to end it here, and I will mention that we are going to talk about how to calculate concentrations. Not today, though. I'm going to give you a little bit of a break because you've got that exam that's due today. So I'm going to stop it here, and I will talk to you very soon.